is an extra box of cookies.
Oh, okay.
So it's an extra box of cookies this afternoon. You're too late.
Why? Because I'm late. All right, awful, awful. Okay. So, should I start?
Yes, please.
Oh, okay. So spin at small x. I'd like to thank the organizers.
Don't forget to thank the organizers.
I have to thank them. Anyway, so as an organizer, I'm giving the talk. Well, A, because the conveners asked me to, but also my collaborators are not here. So Dan was here last week, but was more of a transfer spin week, and he talked about his work with the TMD collaboration there. And Matt is kind of busy moving from one postdoc position to another, so he couldn't come here at all. So I thought I should probably fill in for them and give this talk, give in to the convener's suggestion to give this talk. So this is, of course, going to be a very quick talk, but it will cover a lot of work. So a lot of stuff I'm not gonna give you details on. You know, if you want, we can discuss it more. And it's really based on a number of papers. This is maybe the more recent one in the series, and there are 7 other ones which would be like a homework reading. Okay, it wouldn't be. Anyway, so what's the outline of my talk, if all goes well. So really the goal is what we all would like to have, right? A good understanding of small x asymptotics of all the TMDs. In particular, in my talk, I will concentrate on helicity. And if I have the time, and it is sort of orthogonal to the main thrust of this week, is transversity. Orthogonal in more ways than one. But really what I'll talk about is a mechanism to, at least within perturbation theory, to take any TMD you want and determine its small x asymptotics. So what I'm doing could be applied, you know, pick your favorite TMD and follow the steps of this prescription, and you get the small x asymptotics for that TMD. At least you'll get small x evolution equations, which you then will need to solve, which may or may not be easy, but at least you know what to do to find the small x behavior of different TMDs. Of course, I have to apologize. The techniques I'll talk about will be significantly different from everything we've heard this week. So we're really shifting gears significantly in my talk compared to the previous weeks. Okay, so but anyway, all this aside, I'll start after a brief introduction, which nobody needs here. So I'll be really brief with it. I'll talk about quark helicity, how we can take a quark helicity TMD and massage it at small x to write it in a more convenient way to evolve towards small x. Then we write down small x evolution equations for the TMD, and so by solving them, we'll find the small x asymptotics of quark helicity. And the rest of the talk, if I don't run out of time by that point, the rest of the talk will be sort of repetitive. You take Gluon helicity and you follow the same prescription. You massage the say Gluon helicity TMD at small x. You write it in a form which is convenient to evolve as small x. I'll explain what that means. Write down evolution equations and solve them to find the asymptotics. And then repeat for, say, the valence quark transversity, again, if I have the time. So the goal is maybe not to get through all of that in all the gory details. Feel free to stop me and ask me questions and even criticize me. Not so much, no. Don't criticize me too much, but just ask questions. What? I was late. Yeah, that was already criticism. Right.
But it compensates for cookies, so that is already on.
I was late because I had to like bring everyone cookies and this and that, and move my talk on a stick that actually works. All right. Anyway, for those of you who don't want to hear all this gory detail, these are the main results, right, of my talk. So when dust settles, we'll get the Quark Helicity, you can take Quark Helicity TNDs, or you can take the PDF. The X dependence, the leading X dependence would be the same. So this is applied GNC. This is an important clarification here, but applied GNC will get 1 over X to some power, and that power is given by this expression right here. It's a function of the coupling. And see the number of colors, everything else is numbers, and you can, divide 4 by root 3, it's about 2.31 times the square. For the gluon, we get a different power of 1 over X, a small x in a large NC, which has a different prefactor here. It's 13 over 4 root 3, which gives in the end a slightly smaller number than the number for the quarks. Somehow, amazingly, all those things, the number is of the order of 2, give or take a little bit. And that remains invariant, even if you move next to, say, the valence quark transversity. So this H1T and H1T perp TNDs in a flavor non-singlet channel will get the asymptotics for them, a small x, which is 1 over X to some power. And that power, of course, they are extra suppressed by an extra power of X. That's why the power starts with -1. But other than that, you get the 2 times the square root here. At large and CCF, the fundamental Casimir's and C over 2, so really it's the same square root everywhere. So the factor in front is of the order of 2, but it does vary from TNT to TNT.
What about the software bound?
Software bound, you have to compare this guy, right? It's certainly at low X much smaller than this guy, let's say, and then you have to add the unpolarized one, which is 1 over X to the power of 1 plus, right? So, right, to complete the picture, yeah, I don't want to use too much color in my shell. What?
Go ahead.
Not happy again?
No.
Okay, so this is 1 over X, so the unpolarized one. It's just, say, if you take DFKL evaluation, which is quite fine for the unpolarized one, 1 plus, let's say 4 alpha S NC over pi log 2. Okay, so clearly this is a small x, right? This grows much faster than delta Q and much faster than the transversity. So if software bound is what you take the sum of this and that, on the right hand side should be larger than this. It's easy to satisfy. It actually is not much of a bound. Don't need to criticize software, but in terms of the bound, yeah. Okay. Any other questions?
Why are you saying that? Go ahead. No, go ahead.
There are 4 different people.
So if you say valence quark transversity, you assume there is no C quarks contributing?
No, I don't assume there is no C quarks. I'm just saying that we calculated the valence quark transversity.
So you look to the low X tail from C for the valence.
For the flavor non-singlet, one can ask a legitimate question: what happens to the flavor singlet one? And it just hasn't been done.
Perfect.
I believe the equations will be harder to solve, and it's more of the difficulty level will become comparable to delta Q, which you'll see is quite involved. This is. Our standards is almost a free lunch.
I just wanted to understand what exactly you, but clear, perfectly.
For large NC, meaning of C part. Large NC. Just like not your part.
Yeah, but it's
unless you have some very like Helicity is a special case, but in most cases drops out. Anyway, that's a separate.
Sorry, I'm not sure what your comment is about. Are you talking about flavor? Right. You're talking about flavor singlet or non-singlet?
It doesn't matter. The thing is that when you have the loop is usually.
Quark loops are of course NC suppressed,
right?
But that doesn't have much bearing on what you're saying, because well, you have to create one C quark, right? So if you want to do a singlet distribution, so H1T singlet, I don't know, maybe it's not a very conventional notation, right? So something like U plus U bar plus D bar. Noble says strange quarks don't exist. But if I, so I'm not writing them down.
Would U-bar be suppressed?
No, it wouldn't be. It would be, I mean,
You have the Z graph, only the Z graph coming. You have a beta, you start out.
So it's just gluon driven. You evolve your gluon, and then in the last step, your gluon splits into, say, U and U bar.
But it's one of its coupling is the one.
Yeah, so there will be like,
right?
possibly, well,
but G squared and C is equal to
yeah, but that's just one factor of 1 over C. So, yeah,
okay, depending on how large you take the NCTC infinity, I'm trying to say that that's Z graph.
Yeah, maybe. Look, I mean, I don't want to discuss something I haven't calculated. So there might be one factor of 1 over C suppression because of that. But
yeah.
I have to, compare to maybe non-synthesis. Yeah, maybe. Right, but X dependence, I don't know. Okay, one.
Quick question. So this KT dependence, what do you mean that a small x KT dependent drop or
No. This is just concentrating on the leading power of 1 over X. There is also KT dependent factors multiplying this.
Okay.
So I mean, okay, this is maybe going back to the discussion Monday or something, right? Whether X and KT dependence factor exist. No, they don't. I mean, in general, say if you look at BFK equation, right? This is not an exact solution of BFK equation. Solution of BFK equation, right, is a integral over some parameter mu, which goes along the, well, it's like an omega, right? But you right, so let's go with gamma, right? So then it goes sort of along the axis, along the straight line parallel to the imaginary axis, and then you have some KT squared over, say, KT naught squared to the power of gamma, and then you have e to the alpha s. Well, it depends how you normalize, you can call it 2 alpha s over NC over pi log 1 over x. So this is really just the power of 1 over x times some function chi of gamma. Right? And so say in a leading order BFKL, this would be 2 psi of 1 minus psi of gamma minus psi of 1 minus gamma. The exact form is not very important here, but you see, yes, in the integrand x and KT dependence factorizes, but then you have a convolution, so you have to do the integral. Usually you say, if your x is very small, the integral is dominated by the saddle point of this function, and this is what I write here. Of course, this is just the value of the exponential. If you carefully do the saddle point calculation, so you also get some power of KT, something like, maybe I should switch the notation. You'll get some KT naught over KT, and then you also get the factor, something like log squared KT over KT naught, divided by some number alpha s log 1 over x. So you get this Gaussian distribution with log squared KT. So this term, for instance, has no factorization whatsoever between KT and x. So what I'm saying is, these things here, in principle, also have some KT dependence. I'm just not showing this.
Is there any indication from global analysis that the code delta Q rises like this?
From the data? This is not a question to me.
I checked with Daniel, and I mean, the errors is compatible. So this prediction is compatible with that.
Right, so sorry. So I think, yeah, I mean, oh gosh. All right, so now I have to jump to the backup slides at the end of the talk. So that's very good.
That's probably all you need to do.
That's all I need is observe week.
I kick myself out of the PowerPoint slide. That's not good. So yeah. So I mean, this is some phenomenology we did. Phenomenology, quote unquote, very naive estimates we did. So if you look, so this are delta U and delta S, and I think the solid curves are DSSV 14. And the dashed and dotted lines are our asymptotics. And depending on, so we really just take this power law tail and attach it to the SSV starting from a certain point. And you can see that, well, if you're being conservative and you say that low x means, say, x of 10 to the minus 3 or smaller, then you start from x of 10 to the minus 3 and you just run down this way. That doesn't change much. For strange quarks, we also have a similar plot for delta D, I don't have it. For strange quark, again, if you're conservative, the change is minor. If you're brave, you don't have major differences. And then you do delta sigma, right, by combining all the three flavors. And again, if you're conservative, the change is minor. If you're braver in terms of the X region of small X evolution, you get the more pronounced changes. For gluons, it's actually like, it's even probably less pronounced. So again, this is the same exercise. We take the SSV curve, we take different power laws that we attach to it. And right, I mean, the change is kind of minor. It doesn't go to 0 as fast as the SSV suggests, but in the end of the day, the integral doesn't get affected too much by this. So I don't know if it's an evidence for it, but it's not an evidence against it. Right? It just shows you that it doesn't, probably wouldn't change the phenomenology too much. What's the use? What's the
Probably it's 10
Probably 10. I'm trying to read. I didn't probably put it in one of the previous. Gosh, this is the backup slides. I wasn't reading. Yeah, probably 10. I can get back to you. I think the statement though doesn't change too much.
But the power is something like minus 0.8, right, in the exponent. Is that right? Did I get this computer?
For which one?
For,
The power is, I don't think it's that large, right? So we can go back to the beginning of the talk and plug in the numbers.
Depends a little on the alpha S and plus
Right, so it does take 0.3, then alpha S cancels with pi, and C over 2 is, 1.5, square root gives us 1.2 or something. No,
alpha S doesn't
sorry, alpha S cancels with pi gives us 1/10.
Exactly.
So we have 3 halves, right? So 0.15, square root of 0.15 is about 0.3, 0.4 really, yeah. 0.4 times 2, yeah, no, you're right. It's closer to
Which is
which is what you guys
quite
have,
active.
or-
Well,
or
we
it's-
don't have quite such
yeah,
a
you
large
probably
level, but it's that's why it's finding some effects, of course.
But, of course, I mean, ultimately it's a determinative expansion.
Yeah,
right?
yeah.
One day, maybe us, maybe somebody else will calculate the next term, which would be the alpha S. By the way, it's an expansion in the square root of alpha S.
Yeah.
So you have 30 more minutes.
Yeah.
Good.
It's all about depth. Breadth of the coverage. But
But
I mean,
I
this
would
is the breadth. It covers all the results too.
The transversity signal, I imagine, is not so bad really because there's no one involvement in the evolution. So basically, the splitting functions at lowest order are there's no difference between single and non-single.
Oh, really?
And then at next order, you get the bar mixing piece, which I'm not sure that might be.
Next to leading order and
That's the first time you find any difference at all. So maybe it's not that different.
yeah, maybe. But I don't know. Like I said, I haven't looked at it. I mean, I never thought there was much demand.
Yeah.
Is there a demand for
I think
for
no.
this?
People are looking at tensor charges now.
Mhm.
More interesting now.
Okay.
But
All
anyway,
right. Maybe we'll. Silas, did you have a question?
Yeah, it's not important enough to keep you from making your point.
Well, the point's already made. The rest is just. All right. Okay. Okay. So this is the introduction. Nobody needs. So I'm really, not gonna say anything. Right? We need to understand what happens at small x. To spin, quark spin, gluon spin. So that's the goal. What can we construct the theory input for that? This is blah blah to the same. Here, and the same for transversity, right? We need to understand small x's and products of transversity to, for instance, constrain the temperature better, and then everybody will be very happy or not. Okay, so let's start with quark helicity at small x based on this magnitude of papers. And I'll be concentrating on the flavor singlet case. Here we did calculate flavor non-singlet case, and it's not as interesting as a flavor singlet case. Certainly not related to the spin sample. Okay, so this is the, we'll talk about TMD. So we're talking about Helicity TMD, and we start, so some of you have heard me talk about these issues before, and we wouldn't really do it the proper way. We will start with a CDIS process rather than with a TMD. So actually what's new in sort of maybe formal details here is that we're looking at the operator itself. So this is a Helicity TMD operator. U is some sort of a Wilson line staple, and we're going to take it to be future pointing as in the CDIS staple essentially. And then in working on a particular gauge, so A minus equals 0 gauge for the plus moving proton, the staple becomes just a product of two light cone Wilson lines. And what else? And we can also rewrite this matrix element as a small x type of so-called CGC averaging, where we keep the sort of the epoch parameter, the position of the target proton, fixed, but then we integrate over all the positions. So in averaging, the position of the target proton is fixed, but and then afterwards is integrated over, and we also integrate over the positions zeta and psi of the two work fields. So instead of just doing a shift and putting one of them to 0, we keep each of them integrated over. Anyway, so this is the beast we need to calculate. And how do you calculate this thing? Well, you insert a complete set of states in here. So you have a cut diagram, and then you start looking at what you have. So this is your matrix element to the left of the cut, right? So you have some quark field and a Wilson line attached. So take, for instance, this diagram here. The quark field is at this point, and then you have a future pointing Wilson line which goes all the way into the cut. The other part of this expression is a complex conjugate diagram, right? So you have the anti-quark, the psi bar field at this position psi, and also a Wilson line which goes off to temporal infinity, which again is the same cut. And then you have to consider different situations for different values of zeta and psi. Now you may ask, what is this shaded bar is? Well, this is the proton. This is the proton we need, right? So in other words, we have a proton which is moving in the light cone plus direction. So along the x minus axis, the proton sits roughly at x minus equal to 0. And then we have this operator which comes in, and well, this operator psi, say of zeta. Zeta could be anywhere. It could be to the left of the proton, to the right of the proton, or inside the proton as well. And you have to carefully consider all those situations for zeta and for psi. And that's why we have many different variations. Does this make sense, or did I lose 3/4 of the audience? So, I mean, one could write some sort of a TZ picture. Right, so this is a proton which is moving in x plus direction. And then we have the x minus direction, right? So x minus axis is this one. So you can say that the proton is at x minus equal to 0. And then you're trying to look at the staple, which is, I'm kind of gonna expand it a little bit, right? Which is going to x minus infinity and it's coming back. And those points could be inside the proton. The points where the staple begins and ends could be inside the proton, or they could be outside the proton on either side, right? So you have to explore all those cases for, say, this would be the zeta and this would be the psi.
The transversation,
yeah, the gauge we choose, I briefly mentioned, it's an A minus equals 0 gauge.
That's tapered.
No. It's not the light cone gauge of the proton. It's the light cone gauge of this guy. So for the proton, it's like covariant gauge. All the proton fields in this gauge are localized on this X plus light cone. So there's no fields, right? So if you're worried about this table, there's nothing going this way in that gauge. Okay, so we gauge it away. Okay.
I'm somewhat confused. This language. I thought usually we bring in a Wilson line, it's connecting, for example, in the representations, the side R. If you put this line outside the product, it's not gauging variant. So you should make the gauging variant of the side R and Wilson line between them.
Yeah, so this is side bar.
But you said they're starting to be a different.
Right, I think
outside
perhaps
the
you
product.
will appreciate it a little better when I write in more detail what I mean. So in this slide, I'm just drawing Wilson lines, but I'm not drawing the field sign sidebar. So to you, it seems, oh my God, I have, I don't know, like here, right? We have this, or here, we have this Wilson line which starts in the middle of nowhere. Why does it start? Where is the Quark field which makes engaging there? Of course, what I mean by that is really just that I didn't really draw the whole thing yet. So if I want to explicitly draw what I mean, is this is the diagram of the same B-type that I just showed you in the previous slide, right? So B-type is we have one starting point of the Wilson line is to the left of the shockwave, one is to the right. What is really meant is we have, so this is still, the thick straight line is still the Wilson line, and then we have the Quark fields which come out of the proton one way, and if you wish, the anti-Quark field goes the other way to connect. So really what I have in mind then is a diagram like this, which is fine. You can think of it as some sort of a source current, right, which sources the anti-Quark, I guess, this way, and the Wilson line. So the momentum would be conserved. It doesn't need to yet interact with a proton, and then those things interact with a proton. Box here means some spin-dependent interaction, and then we can have them recombined there. Okay, so don't worry, gauge invariance is fine. Okay, any other questions? Yeah. All right, so we consider all those different situations, and then we really want to understand what we mean by them. So we really draw actual Feynman diagrams in more detail, as shown here. And well, here are the situations. And you say, oh my God, that's a lot of diagrams to calculate. Well, you can start with easy ones. You look at diagram D, right? Yeah, you can draw a Quark loop here, but nothing in the end interacts with a proton here. So you say, oh, there's no way this diagram can know anything about the spin of the proton, so we don't need to calculate. And you throw it away. You look at diagram C, yes, you may have some spin-dependent interaction with the proton, but actually you can argue that you can take each of these T-channel quarks, move it across the cut left and right, and all those interactions would cancel. In the end of the day, again, no spin will be transferred in the diagram C, so diagram C is also discarded. Then if you did small x calculations for a while, you can argue that the diagram F is actually energy or extra x suppressed compared to everything else, and it can also be discarded. And then you're left with diagrams A, B, and E. And then I'm going to spare you the pain of the calculation, but you can argue that at least in a leading double log approximation I'm working in, diagrams A and E actually would cancel each other. And one is really left with the diagram B to calculate. So bottom line is that's all we have to calculate. And one can make a connection to the CDIS process. So CDIS process at small x doesn't look like what people usually draw, right? So the standard quote-unquote CDIS process would be you have a photon come in and interact, enter this vertex, produce a quark, essentially knock out the quark out of the proton, right, with this instantaneous type of an interaction, and then you square it. That's your CDIS process. At small x, this is not the dominant process. At small x, you have a photon, virtual photon come in and split in the QQ bar pair, which then interacts with the shaded area. Sorry, it's somehow oversaturated, so it's still dark here. But this is again the same proton that one interacts with. And again, the splitting may happen before or after the proton shock wave. So, for instance, here we have the splitting after the shock wave. Here we have before, so we have interference terms And you can also argue that the cases where the splittings happened before give no spin dependence, and the second type gives a stance. Anyway, those are technical details. Bottom line, whether you calculate the CD's cross-section or you start with the operator at small x, you're only left with this object here. So you really have to calculate the interaction of an iconal quark, which is this Wilson line, the thick Wilson line, and the anti-quark, which interacts in a spin-dependent way with the proton, right? We need the spin-dependent interaction. We're looking at helicity distribution. Wilson line is just an iconal Wilson line, knows nothing about spin. Okay? So we have something which we refer to as a dipole. We have a quark line and an anti-quark line, and the color singlet state initially and finally. And it has to interact in a spin-dependent way with the proton. Okay? And the rest of the diagram is easy to calculate. This, if you wish, the splitting here and the splitting there. At the end of the day, we end up with an expression like this, where we have integrations of various transverse positions of the quark and the anti-quark in this dipole. I'll explain what this amplitude G is, but really G contains the interaction which we need to calculate here. G is the unknown, and everything else is just some transverse position convolution and the integral over the longitudinal momentum fraction carried by, say, this guy, this anti-quark line down here. Okay? So the bottom line, I don't want to again dwell on it too much, but so we have to say the quark helicity TMD at small x is really related to something which we call the polarized amplitude, polarized dipole amplitude G. Okay, so this G amplitude is defined in the following way. You take, so this was our original Wilson line, just the iconal line, and this is the anti-quark line which interacted in a spin-dependent way. And actually, if you do the calculation more carefully, you also need to add the contribution where the polarized line is a quark line and the Wilson line is the anti-quark line. And you have this operator here where V naught is just the Wilson line, light cone Wilson line, good old one, which knows nothing about spin. And the spin-dependent polarization sits in this V1 polarized. It's an operator which contains a quark, which is a high-energy quark, but has some non-iconal spin-dependent interaction with the target. Okay? And we take a trace and average it. So this double angle averaging is different from standard averaging before, which was a single angle averaging because I scaled out the center of mass energy. And Z is the longitudinal momentum fraction carried by the polarized line here. So you say we have this dipole overall carries some plus momentum, right? It's a dipole moving, I'm sorry, it carries some minus momentum in this line, which is moving along the x minus direction. And it's that minus momentum is distributed such that the anti-quark, say in this case, carries fraction Z, and the quark carries the fraction of 1 minus.
What does the V1 look like?
What does V1 look like? That's a very good question, and this is the next step. So at the moment, I'm just saying it's some high energy amplitudes for a quark to interact with in a spin-dependent way with a target. And actually, you can get by with it quite well, but if you really want to understand it in all detail, you have to write an explicit expression for V1. Okay. So to do that, you take a high energy quark and you send it through a target. And of course, at least one interaction should be subiconal because I want the part of the high energy scattering amplitude which depends on the helicity, right? I'm after helicity. I don't want to just have the leading iconal interaction which knows nothing about spin. That's what I know how to do very well, but that's not the observable we're interested in here. So you may have, so the target in a standard small x approach or saturation approach, you can think of it as made out of many different nucleons. You can think of it as a nucleus if that makes your life simpler, or think of this just as individual quarks somewhere inside the big fat proton. And the point is that the quark can go and interact iconally as many times as it wants with those quarks. That doesn't change anything, but at least one interaction, which is denoted by these blobs, right? So the blob vertices are subiconal vertices, subiconal quark gluon vertices. So at least one interaction should be spin dependent, okay, to transfer the spin. And after this one interaction is done, transferring the spin information, it can again interact many times in an iconal way. Of course, exchanging gluon is not the only way to transfer spin information. We may have quark exchanges, in which case you actually need two T-channel quark exchanges. So you have a quark which comes in, kind of exchanges a quark with a target and becomes a gluon, and then gains another quark from the target and becomes a quark again. Okay? So you have to calculate these processes, concentrating on helicity-dependent terms, and shoving a lot of calculations under the rug, we arrive at this object here. Remember, these are just usual Wilson lines. So we have a Wilson line which goes from -infinity to the point of interaction here, x minus. Then there is this point of interaction which brings in an operator which just measures F12 component, so the 1,2 component of the field strength tensor F minimum of this gluon field of the target. And then after that, the gluon again interacts iconally, so again we have this iconal Wilson line. And we integrate over this point x minus where this non-iconal interaction can happen. It could be anywhere, right, along the x minus axis. Of course, it should be, it better be within, well, related to the position of the proton, but we integrate over all x minus, and there is some prefactor. And we have this term here, which results in a slightly more complicated object here. So V is a fundamental Wilson line, U is an adjoint Wilson line. So since we also have a gluon propagating and interacting iconally here, we have the gluon Wilson line. Otherwise, there's a gamma matrix structure, which is familiar to everyone who knows and loves, you know, longitudinal spin. So there is a gamma plus gamma 5, which comes out. It's not being put in by hand. It's really, we just do the calculation, and we get this operator. So now we know everything, right? We know what the polarized operator V is, and we have the standard unpolarized Wilson lines. And we can now talk about deriving small x asymptotics of this evolution. By the way, the physical insight here, what is this F12, right? Why is this F12? This is just mu dot B, right? So if you have a particle with some magnetic moment mu propagating in a magnetic field B, the strength of the interaction is mu dot B. In our case, we're talking about longitudinally polarized quarks, so mu is in the z direction, so mu dot B is mu z times bz, and the z component of the magnetic field is just F12. So this is very heartwarming, right, that you do a complicated field theoretical calculation and you get the physics 101 result. So that's, you know, usually there is a disconnect, right, between the QFC calculations and the stuff you learn as an undergrad. No, I don't know why I took this, because I kind of like it better. No, I think batteries are still good. Okay. I may need batteries, the pointer not so much. Okay. All right, to complete the picture, and I'm not going to bore you with the details. Yeah, so I actually had an expression here. This is a adjoint Wilson line. So it's just also like on Wilson line, but with a adjoint gluon. We also have high energy gluons in this game, so we have to do the same calculation for this adjoint polarized operator. Again, a gluon interacting in a non-iconal way, either by exchanging a gluon or a pair of quarks. And you get something very similar. Again, there is F12, it's calligraphic because that's our notation for adjoint fields. Okay, so we have this dipole operator. We know what V0 is. We derived V1, so we know exactly what it is, and we want to evolve it in small x. But evolution equations are very complicated in general. So as is customary in small x physics, at least in the saturation approach, we can first take the Lagrange C limit and explore it first. In the Lagrange C limit, you can you can have a dipole made out of quarks. That's this dipole amplitude G that we talked about here. You may also have a dipole made out of a pair of gluons, and the relation between the two is very simple. One is 4 times the other. Some of you may know the unpolarized situation where the coefficient is 2, but for this polarized amplitudes, the coefficient is 4. So anyway, bottom line, all we need to do is write down an evolution equation for this G, and then we could find out, say, the other dipoles. So how do we write evolution equations for dipoles? Well, you say, okay, this is our dipole. It is equal to some initial condition, some homogeneous term, plus you start including one loop corrections. So for instance, so the box here means it's not non-iconal spin-dependent interaction. How can it proceed? It can proceed through this gluon emission with a spin-dependent interaction here, and one of the vertices emitting the gluon being non-iconal. There are variations of this diagram. Or you may have just an iconal gluon, and then the quark which was coming, the gluon which was coming in continues on to interact in a non-iconal way with the target. So this is really how you write the evolution equations. Is very similar in a way, but there are some important differences from the to the unpolarized small x evolution case. All these gluons are very long-lived. They're always emitted and absorbed on different sides of the shock wave. They have to be long-lived to generate logs of x, right? We're interested in resumming logs of 1 over x corrections. And why, I don't think I have the time to explain this in more detail, but just trust me that you don't have any emissions inside the shock. All right, so when dust settles, you get an evolution equation for this G. So this G is related to the one we had before by just integration over all impact parameters. So but anyway, we have an equation for G, and there's some auxiliary function gamma. Again, I don't have the time to talk about where it comes from, but you have these coupled equations. Once you solve it, you find G. Once you have G, that's all you need to find your Quark Helicity TMD. Initial conditions can be given by just lowest order interactions with the target, 2 gluon exchange or 2 quark exchanges. And those could be easily calculated. All right, now what's my resummation parameter? Say DFK evolution we talked about earlier. DFK evolution resums powers of alpha s log 1 over x. And you can see it, yes ma'am, 5 minutes? Okay.
Continue.
That's fine. Okay, good. All right. So you can see here, right? We have alpha s times log 1 over x. They enter together, and this is a resummation parameter. We resum all powers of this quantity. What are we doing? So that was an unpolarized case, right? For unpolarized TMDs like F1Q or F1G. Here we actually have a different parameter. So for helicity evolution, the parameter is alpha s times 2 powers of log 1 over x. Again, I don't have the time to talk about details, especially with a 5-minute cutoff coming up on here. But the point is, where does the second log come from? So one log comes from the integral over longitudinal momentum. The second log, in the case of of this helicity evolution, comes from the integration of the transverse momentum. In the unpolarized evolution, transverse momentum integration does not generate a log of energy over 1 over x. Here, for helicity evolution, it does. Okay, and that was known before. We by far are the first ones to talk about this resummation parameter. It dates back to works by Kirchner and Lipatov in the early 80s. Okay, again, skipping a lot of technical details, right? So 2 slides ago, I had evolution equations with some initial conditions. I can solve them. So that's what we did first numerically. We plugged in Chad. So this is a log of G as a function of something related to some function of transverse size of the dipole. And eta is really like log 1 over x. So high energy is this way. Dipole size varies here. We solved this thing numerically. These equations found G numerically. And then really what's there that it realized that this is really just a plane, right? It's a flat triangle. So there is scaling in the problem. Using that scaling, we solved the equations exactly analytically and obtained this power that we already saw in one of my earlier slides. So this is the end of the day. Where they talk about Quark Helicity TMD or PDF, we get this power right here. So first we had numerically 2.31, and then we realized after we found the analytic solution, we got 4 over root 3. You can use your Quark calculator to check that this is the first 2.3.
So is this power law a consequence large N? In other words, if you include in those evolution equations some 1 over n correction and purgation theory, would that really would that give you a new function of x, or would it just modify the exponent?
So I don't yet know the full answer to your question, but that's a very good question because it allows me to show a few more slides, and I'll give it an object. So you don't have to take Lagrange C, you can also take Lagrange C and an F, and also get a closed system of equations. So the problem here is if you don't take the Lagrange C limit, you get an equation where you have an operator on the left-hand side and a different operator with modules and lines on the right-hand side. You don't know how to relate them, so you cannot solve. Right? You have two different unknowns on different sides of the equation. Legend C limit allows you to simplify the operator on the right-hand side, right, in terms of operators on the left-hand side, and you get closed equations. So in this case, in this helicity evolution case, you can also take the legend C and an F limit. So, you know, like alpha and C is constant, alpha and F is constant, but then C and an F go to, right? In which case you start retaining Quark loops that K-Fay was asking about. So your evolution gets more complicated, you get Quark loops. So that's one way of going beyond legend C limits. So I'm trying to answer your question. It's not really, I'm not really beating around the bush so much here. But so you get a different set of equations. They look much scarier. I haven't solved them yet. I had a student who, unfortunately, it didn't work out, but he did the preliminary solution, and he found also, in addition to this 1 over x power, he found some oscillation. And I think I mentioned it one of the days that the small x we may not just get the power of 1 over x, but an oscillation. In other words, the sign changing function of x. So if you go beyond the legend C limit to a legend C and an F limit, right? So in other words, if you include this type of corrections to all orders, the power remains roughly the same, but again, the precision of the numerics as it was done so far didn't allow us to really say if it's exactly the same or not. So you get, but the bottom line is you get, you get this power multiplied by something like a cosine of log 1 over x or something. So you actually start having oscillations. So if you, I don't know, if you plot it, we haven't really plotted this, but say you have delta Q, right, as a function of log 1 over x. So you have some sort of a 1 over x type of power at legend C, and it may be that going beyond legend C would also introduce some sort of oscillation with that power given the amplitude. So bottom line is, as you can see, I don't have a good solid answer to your question, and this is why those equations I get to solve.
But that would be good, right? Because it would decrease the importance of below x. Right?
Would it be good or bad?
I think it's good. I mean, in some sense, because if you're after like constraining first moments experimentally, then anything that doesn't contribute much from, say, x below 1 over
okay, good in terms of, yeah, analyzing, being consistent with the data. Yeah, it may be. I don't know if it would necessarily integrate. I mean, I don't know if it's just a cosine of log 1 over x. It's some sort of oscillation. We didn't even have a precise numerical solution to go and start doing the analytic solution. Maybe, yeah, but a priori it sounds like it may integrate out to 0. Yeah, that is okay. Since I probably have 0 time, and I should be a responsible organizer, so let me just say that.
I'm nice to give you 3-5 more minutes. There were a lot of questions.
Okay. 3 times 5.
No.
3 to the 5th power more minutes.
9.
No.
Anyway, this is all repetitive. Gluon helicity, the story is the same, and I'm not going to go into too many details. You start with the operator. The operator, of course, is different. F plus I, F plus J, anti-symmetrized with Wilson lines. We took the dipole definition of Gluon helicity TMP. So our staples go to the plus infinity and minus infinity. And this I and J are insertions of F plus I and F plus J. And this is the proton. So this picture is very similar to the one on the board there, just now for the Gluon. Again, you massage it as small x, you massage it, and we thought we would get the same operator as this V1 polarized that I had before, but no, we get something different. We get an operator, we get this dipole TMT related to a different dipole amplitude, which now has a transverse index J, which actually just has an insertion of a transverse Gluon field, not F12, but just a transverse Gluon field. And so it's a different beast. So we had to write a new set of evolution equations for this new amplitude GI10. Before I just had G10, no I. Now I have an I, and that's for reasons different. Animal. Okay, so we can blah blah about the validity of calling this a dipole. Gluon Helicity TMD if it's not related to the dipole amplitude, but that's a philosophical discussion we can save for another program. But in the end of the day, you write new evolution equation with this I for this GI10. So it's very similar to what we did before, but just details of the calculation are different because you have different vertices with this E sub I insertion. You get new set of evolution equations. They look even scarier than before, but armed with the experience we had. Oh yes, and they mix quarks and gluons. So actually before, right, when I talked about the quarks, the evolution equation for quarks never cared about this new operator for the gluon. But the evolution equations for the gluon do depend on the operator we have, this dipole operator for the quarks. So there is some quark-gluon mixing here, but no mixing of gluons into quark evolution. You set some initial conditions for the evolution equations, again at the Born level, and then you solve them. We actually solve them analytically. I'm not going to talk about how, and in the end of the day, we get this power again that we have already seen, whether it's the Gluon TMD or the Gluon Helicity TMD or the Gluon Helicity TMD. Okay, so and then in the remaining 0 minutes, you talk about transversity. Again, it's the same story. You take the operator, you do the same trick as we did for Helicity in terms of diagram analysis. You massage and you relate your transversity. Or the TMDs which enter into your transversity, you relate it to a new dipole amplitude, which in a flavor non-single case is the difference between the two traces, not the sum. You write the evolution. Okay, so you have to write a new polarized cross-section, which depends for a quark scattering on target, which depends on the transverse spin. So it's a different calculation. You get something ugly and nasty, but I think this is still mu D here for the gluon exchange. And you write down an evolution equation for this amplitude T, which is much simpler. This is an evolution equation even your undergraduate REU student can solve in a week or two. But you solve it and you get the result that you've seen before. So that's really the end of the story. You could plug in the numbers, but it's a very, very small power of 1 over x, if you wish, right? Large power over x for transversity. So the conclusions are pretty much the same as the initial slide. So we have the small x asymptotics for delta Q, delta G, and valence quark transversity. And of course, like I was describing answering analysis questions, if you take the large CNF equations, you may also get some oscillating factors multiplying these powers of 1 over x. This is to be determined. One can ask the same questions about other TMDs. So Yoshi and I are currently looking at OAM at small x, what happens to it in the same framework. But take your favorite TMD, follow our prescription, and you can derive the small x asymptotics of it as well. And since we need to have an EIC connection, of course, this is all very much related to what EIC can measure and hopefully will measure and constrain. All right, thank you very much.
Okay, thank you.
You're the boss.
Yes, Werner and yes, first one.
2 questions actually. So.
Oh,
It's very brief. So one is, I think I've asked it before and you gave me an answer, but some of this, some of the double logs you're computing or you're summing are known by explicit calculation to say next to next or whatever from master. Just that, how can you compare to that?
Right. So we recovered DGLAB splitting function as small x up to n.
Okay.
So we started working on this project in 2015. We spent much of 2016. So the work papers by, I had one of the slides, I didn't have the time to mention it. There were works by Bartels and collaborators back in the mid-90s looking at, I believe, Gluon structure function. And they got, in the end, a different power. So their number there was not of order 2, but closer to 4.
Right. It was
3.6 in the legends, 3.66 in the legends.
Right.
All right. And, we would contact them, and of course, they had forgotten everything about what they did. Bartels kept promising to get back to me, and then we did. We, in the end of the day, tried really figuring out what's wrong with our paper, and just to cross-check ourselves as well, we calculated the anomaly dimensions because they did it as well.
Yeah.
So at least in large NC limit, we calculated delta PGG at next to leading order, and we agree with the literature.
Right.
We didn't go beyond it. It's possible, but it just almost becomes a separate project.
Yeah, I know it must be tough, but I super really nail down things.
Right, but just to complete the story, our understanding is that Bartels and company forgot one phase space contribution of a particular diagram. We didn't forget the diagram, but I was worried. We worried that there is a certain phase space region which they didn't.
I think Matt explained that to me once.
But they can't. Bartels is retired. Riskin doesn't care. Yamalaev admitted that they're wrong, but he did it too easy. Sure. So all this.
Okay.
I mean, turning this around in
nail it
cases where you don't know anything even beyond the environment, orbital, you could use that to predict contributions to that bigger functions at higher orders, right?
I think delta P's are known up to 3 or 4 loops.
They're known to 3 loops.
3 loops.
Right.
You're
But in
saying,
some
yeah,
cases,
because looking at the small x,
right.
yes.
Transversity is 2 loops, orbital is just 1 loop, right? So you could make predictions for some things that you really don't know anything. And the other question I had is very brief. There's no notion of a factorization scheme in this, right? In the sense that it would be the same for, say, MS bar or EIS scheme or whatever we are using in the alternative calculations.
Right, so we didn't get even to the point where we have any UV divergences which require counter term n. For us, so far, all the divergences are cut off by energy, and that's what generates loads of energy. I presume if we want to calculate the correction to it, we'll have to start worrying about how to regulate the infinities, and then we'll probably use them as well.
One more question, and then we
Silence and this kind of first, there's one question between silence and Simonet.
Sort of elementary, I guess, as an outsider. I mean, in looking at these formulas, and I think of the distance scales here as being, say, 1 over q on the target, and 1 over, say, x times the mass of the target. And so, of course, you're in the limit where 1 over q is very small, right? And so of course, that alpha is small. So, am I to understand when you say small x, that you, with respect to the constant wavelength of the target, that these results are valid for arbitrarily long distance scales? So, or is this some intermediate range of x where you're saying within that intermediate range of x, x is small?
So in terms of distance scales, so the distance in the x minus direction is long.
This is more just physically. I mean, is this? Are these results expected to be the answer at large n?
really in order of time because
so
arbitrarily small x.
So really quickly at small x usually you have interactions like this. So if this is your DAS, I don't know, total cross section, this distance here is of the order of 1 over q that you refer to. This distance is 1 over 2mx. So at small x, this is a very long distance. And this is not specific to large NC. So, and then that's why lattice people have trouble because this 1 over 2mx could be, with hundreds of thousands of Fermis, right? You need really big lattices to calculate.
But the point is that these results are expected to be valid for arbitrary.
At extremely small x, you have saturation.
Gentlemen, I cut you off
Which is
now.
not accounted for.
Which is accounted for in the full calculation, not in my presentation. But yeah, those powers do not include saturation. Saturation will just kill the powers.
We have one more talk and we have a discussion session this afternoon.
I wanted to ask about, but this is, we can talk in that discussion.
Yeah, exactly.
It was about transversity from GPDs.
All right.
And so how can you bring this thing forward? But this is,
Yes.
Okay.
I think that is even more, that's
framework.
probably indeed something extra. So I really would like to move on and hear Brendan because his talk is as a preparation for this afternoon. So I think that